So we could say that the osmolarity of the filtrate increases. The osmolarity is a reflection of the number of particles dissolved, for instance, in a liter of water. So that osmolarity increases as we move down deeper into the medulla, as we move down the descending limb of the lumen. So here we see the osmolarity of filtrate here within the cortex is 300, which is very similar to the osmolarity of blood. Okay? And that's partly because water and most of the solutes within the plasma are freely filtered. So osmolarity is much different. But as we move down the thin descending limb of the lumen family, look what happens to the osmolarity, the solute concentration. It progressively increases down to a max of about 1,200, what are called milliosmoles. Okay? So solute concentration increases tremendously because as we move down the thin descending limb, more and more water gets reabsorbed. So you see this gradient developing, where the filtrate osmolarity is progressively increasing down to a max of about 1,200. So the osmolarity is about 4 times what it is in the cortex, way down here.
So Dr. Penner, earlier you said the water follows the sodium. Have you,
Well, what's going to happen is that the reason that the water is leaving is because the sodium and other solute, its concentration in the interstitium is high. So water is following its osmolar gradient.
Okay, and the water, okay.
But the salt can't follow in this case. But water's following the salt that's in the interstitium. Now, once we turn the corner, we come around that half-pin turn and we come back up, then we're going to reach an area in which the epithelium transitions back to a simple cuboidal. This is called the thick ascending limb. So this filtrate is now moving up the thick ascending limb. In the thick ascending limb, the situation is opposite to what we have in the thin descending limb. In other words, once we reach the thick ascending limb, water can't be reabsorbed. We don't have any aquaporins. So water reabsorption stops due to the absence of aquaporins. Now, this epithelium lacks a brush border, but it does have occasional microvilli. Okay? And along those microvilli, okay, you have ion channels, you have protein carriers, that are capable of secondary active transport, meaning they're capable of reabsorbing sodium plus something else. Okay? If they're symporters, or moving two things in the opposite direction if they're antiporters. Okay? So along the thick ascending limb, you reacquire these pumps along the basolateral membrane that can reabsorb sodium into the interstitium. Okay? And along the luminal membrane, you reacquire those protein carriers, those symporters and antiporters. Okay? So what that tells you is that along the thick ascending limb, we can reabsorb solute. Water can't follow, though, because we don't have aquaporins. If it could, it would, but it can't, because there are no aquaporins, openings that allow movement of water. Remember, these carriers and pumps are specific for solutes dissolved within water, but not for the water itself. Okay? So, diffusion of water is going to be very restricted. Okay? So, we have a high solute load that forms here at the hairpin turn. Remember, we said there's an osmolarity of about 1,200. So there's a lot of salt and solutes that are kind of making the turn and reach in here to the thick ascending limb. When we reach the thick ascending limb, we have the proteins now to take a lot of that solute that's formed and then begin to pump it out into the interstitium. Okay. As we pump sodium out into the interstitium and leave water behind, then as that filtrate moves up the thick ascending limb, it becomes progressively less concentrated. That makes sense, huh? Because we're removing solute and leaving behind water. So filtrate osmolarity is going to decrease. Now, there's more salt available to dump into the interstitium the deeper down within the pyramid you are. As we begin to dump salt into the interstitium, there's less available to reabsorb higher up. Okay? What's going to happen is, as salt is being reabsorbed, okay, we're going to develop a gradient between the lumen of the tubule and the interstitial fluid. Let's go back. Okay? For instance, way up here, okay, as you dump salt out along the proximal part of this thick ascending limb, what's going to happen to the osmolarity of this filtrate? It's going to fall. And yet, as we're dumping salt out, the osmolarity within the interstitium is going to increase. So here's an osmolarity of 700. As this filtrate moves up and salt is dumped out, okay, then this osmolarity is going to decrease further, 500, whereas in the interstitium, where we're dumping the salt, the osmolarity is going to increase. Okay. Here's the interstitial osmolarity here, 900. Here's the ascending limb, 700, 600 versus 400. We're developing a 200 milliosmol gradient all along the ascending limb because we're dumping solute out into the interstitium, but we're not carrying water with it. So it's going to result in a 200 milliosmol gradient. And of course, as we move up the pyramid and there's less salt to dump out, we're developing also a medullary gradient, where the interstitial osmolarity gets progressively lower the higher up the pyramid we move. Or we can think of it in the opposite way. The interstitial osmolarity increases as we move down the pyramid toward the papilla. Okay? Now look what happens. By the time we reach the cortex again, instead of the osmolarity being 300 the way it was at the onset, here within the PCT, the osmolarity is down to 100. Okay? Why? Because we're losing salt from the filtrate as we move up. So this slide just summarizes what we've said already, is that the epithelium transitions to cuboidal cells, water permeability is decreased due to lack of aquaporins, and then we still have those channels and secondary active transporters that are available to move solute. We said that we reacquire sodium-potassium ATPase pumps, okay, along the basolateral membrane, and that's what's going to drive reabsorption here. Okay? But because you're restricting movement of water, you're not going to see an equilibrium in terms of osmolarity between the tubular fluid and the interstitium. If water could move freely, then the concentration of solute would be the same, but water's being restricted, and so we're not going to achieve that equilibrium. Yeah, this solute osmolarity is creating that osmotic force that's pulling on water, but there's no aquaporins that allow the water to follow the salt. Okay? So we're developing an osmotic gradient between the interstitial fluid and the tubular filtrate of about 200 milliosmoles. And this just shows an example of what's occurring in the thick ascending limb. Okay? This is the lumen of the tubule. These are the cells. This is the bloodstream. You've reacquired these sodium-potassium ATPase pumps. Okay, that's moving sodium out into the interstitium and ultimately back to the bloodstream. And at the same time, you're developing an electrochemical gradient that's facilitating the movement of sodium out of the filtrate and into the cell. Remember, this is an electrochemical gradient. Notice it's moving along a symporter. That symporter is also ferrying chloride and potassium. So we're moving solute from the lumen into the cell, and then from the cell into the interstitium. So the filtrate is becoming diluted as it's moving up the thick ascending limb. At the same time, we're developing increased interstitial osmolarity, about 200 milliosmoles greater than the filtrate at any one level. Okay? And then on top of that, as we move down the medulla, we're developing this medullary osmotic gradient, okay, where the concentration here is 300, 500, 700, 900, maybe 1200. Osmolarity progressively increases as you move down the medulla. Okay? This is an important concept. This medullary osmotic gradient, and we're going to see this next class, is what allows us to concentrate our urine. Okay? So the buildup of this gradient that occurs within the thick ascending limb is what later is going to allow us to concentrate urine. Okay? If we're, for instance, volume depleted or dehydrated. Okay?
Dr. Pinner, is that why the interstitial osmolarity never evens out? Because I feel like as you keep on giving...
Right, because it's never going to be
It's never going to
the
reach.
same.
Okay.
Because we keep that the same process keeps repeating itself. Okay, so I think that's where we'll stop today. Now, let's do this. Let's plan for a quiz on Monday. We haven't had a quiz in a while. So we'll plan for a quiz on Monday.
Well,